For chapter 4, we're going to talk about chemical reactions and chemical quantities. Chemical reaction is when a new compound is formed. And usually involves an exchange of atoms, but you can have other things like a precipitation reaction where not necessarily atoms are exchanged, but ions form new compounds. And specifically combustion, quite a bit of chemical reactions are combustion. This is when an oxidizer reacts with fuel. Usually the oxidizer is oxygen and typically emits heat. So with chemical equations, one of the most basic is on the left side of the equation are the reactants, and the direction of the reaction, and then the right side of the equation is the products. So some information we have in there are the formulas of the reactants and products, so the chemical formulas, the states of them, solid, liquid, gas, aqueous, and the relative numbers for balanced chemical equations. So here are the abbreviations: gas for lowercase g, liquid for lowercase l, s for lowercase solid, lowercase s for solid, and aq for aqueous, sometimes aqueous as well, but that means dissolved in water. And water is very important for many things like biological processes and the large amount of water that we have here on Earth. So water is a very important state, things to be dissolved in water. So let's start off with combustion of methane. And so methane is a gas, typically referred to as natural gas, burns to form carbon dioxide and water. So we have this equation here. This is methane, CH4. That means carbon with 4 hydrogens. The subscript 4 means 4 hydrogens. It's in the gas phase with oxygen, so O2, diatomic oxygen, in gas phase forms carbon dioxide with 1 carbon, 2 oxygens, molecule in the gas phase, and water, 2 hydrogens and 1 oxygen also in the gas phase. There's a problem here because the number of atoms on the left do not equal the number of atoms on the right. So we have to balance them. So if we start off here, to balance a chemical equation, you can see the oxygens and the hydrogens are already misbalanced. So how do we balance this? We look at the carbons. The carbons are the same on both sides. There's 4 hydrogens on the left, and there's 2 in the water, so we need to multiply the hydrogen or by the water by 2. Now notice that you cannot change that to H4O. That's a new molecule, so you can't change the subscripts because then you change the chemical reaction. So you have to include the 2 there. And now there are 2 oxygens on the left and 4 on the right. So how do you get around that? You put a 2 in front of the oxygen, 2 in front of the O2. Now it's balanced, and you can see here with this picture, it shows that there are 4 hydrogens on both sides, 4 oxygens on both sides, and 1 carbon on both sides. So how many oxygen atoms on the right hand of the following chemical equations? So we have 2 Fe2O3s, so 2 times 3 for the O3s, that's 6, what's in the iron 3 oxide, and then 4 CO2s, 4 times 2 is 8, so 6 plus 8 is 14. That's how you do that. Which quantity or quantities must always be the same on both sides of the chemical reaction? It's the atoms of each specific element. So it's that one. Reaction stoichiometry, how much carbon dioxide? So we look at this balanced chemical equation for octane. So, and you can see that 1 molecule of octane, it's a 1 to 8 ratio or 2 to 16. So there's a huge amount of carbon dioxide formed. With that, carbon dioxide is 44 grams per mole, so that means that there's going to be a great increase in the amount of carbon dioxide in terms of mass versus the carbon fuel that you're burning. So in chemical reactions, follow a couple things. Law of conservation of mass. Matter is neither created nor destroyed. And balancing the chemical equations by balancing the atoms, and each atom is about the same mass. I know that terrestrial averages, but going through all of it, the amount of matter in the reactants is equal to the amount of matter in the products. So, and these ratios between the different reactants and products, this is known as stoichiometry. So it is the chemical accounting. And so for instance here, look at this reaction. 2 octanes plus 25 oxygens make 16 carbon dioxides and 18 waters. So that is saying 2 molecules of octane react with 25 molecules of oxygen to diatomic oxygen to form 16 molecules of carbon dioxide and 18 molecules of oxygen, or 18 molecules of water. And you can look at that as moles as well. And molecules, moles, the ratios don't change. So let's change topics, and what I'm going to build up to is a concept called the limiting reagent. So the number of pizzas that you have depends on the amount of materials you have. And here's the recipe for a pizza. It's a crust, 5 ounces tomato sauce, 2 cups of cheese makes a pizza. So you have these ratios here, the reactants, 1 part crust, 5 parts sauce to 2 cups cheese makes 1 product part pizza. So reactants on the left, product on the right. And from this, how can we, if we have 10 cups of cheese, how many pizzas can we make? Well, if we need 2 cups of cheese for each pizza, that means that we can use the ratio of pizza to cheese to figure out how many pizzas we can make from that. And from that analogy, we can apply that to chemicals and chemical reactions as well. So instead of making pizza, this time we're making carbon dioxide and water from octane and oxygen. And we have the ratio, for instance, of octane to carbon dioxide. It's 2 to 16 or 1 to 8. And then if we have 22 moles of octane, how many moles of carbon dioxide? Well, we can use that ratio and we get 176 for that. And you can also do this for mass. So and I know we're starting with moles, but moles is a really cumbersome value. I mean, typically we measure things in mass. I mean, it's just easier to put things on the scale and measure mass. We don't measure moles directly, right? We measure mass. And instead of that, we can use dimensional analysis to figure out the answer. So let's do this. Balance equation here. How many moles of water are produced by the combustion of 22 moles of octane? Well, I mean, you can see it's a 1 to 9 ratio, or 2 to 18 for water. So it's 22 times 9, and that's going to be 198. So mass to mass, here's an example with that. If we burn that many grams of octane, how many grams of carbon dioxide form? Well, we have to start by getting the molar mass. So this is like when you attack a problem. You got to look at the given information, look what you need. The given information here is we have 3.7 times 10 to the 15 grams of octane. And we're trying to find out what mass of carbon dioxide are formed. So we got to get there, we got to get dimensional analysis, and we have a balanced chemical equation. So, but we need to turn mass of octane to moles of octane, then we got to convert between moles of octane to moles of carbon dioxide, and then we got to multiply by the molecular weight of carbon dioxide. And so from that we can get the, from that we can go through the dimensional analysis, and we find out that we produce 1.1 times 10 to the 16 grams of carbon dioxide. Okay, so under certain conditions, let's look at this conceptual connection here. 4 sodiums plus oxygen makes 2 sodium oxides. And we have 3 molecules of oxygen. So if we have 3 molecules of oxygen, that means that we have a 4 to 1, so that's going to be 4 times 3. So that means we have 12 sodiums, and so we need 12 sodiums to do that, and the answer is C. Another one here, consider this equation here, A plus 3B makes 2C. We have, let the circulars have A, and which one are we going to react for that amount of B? So we got to count that, so 3, 6, 9. So we have 12 molecules of that, so 12, so that means we need 4 molecules of A. So, and that's what we got for there. So you got to count that and then apply the the 3-to-1 ratio. So there's 12 molecules of B, and there's a 3-to-1 ratio. So then that means you need 12 divided by 3 or 4. Okay, so going back to limiting reagent, so we have the pizzas. If you remember here, we have the pizzas, and we can look at things. We were looking at cheese before, but what if we, let's say that we have 4 crusts, and we have 10 cups of cheese, and we have enough tomato sauce to make, we have 15 ounces of tomato sauce, so that's enough to make 3 pizzas. So if we have enough crust to make 4 pizzas, and we have enough cheese to make 5 pizzas, and we have enough sauce to make 3 pizzas, how many pizzas can we make? We can only make 3, right? Because we go by the smallest amount. So in this case, the amount of tomato sauce is the limiting reagent for our making of pizzas. And so that you always go for the lowest. And for this, I mean, what do you say? 10. What if we had the cups? Like we made 5 pizzas. Well, there's not enough matter. There's just not enough. You can't create matter out of nothing. And the reason for this is it's the conservation of mass. So theoretical yield. Things are not always perfect. We have the limiting reagent, and we can figure out what the theoretical yield is. That's the most we can make of something. But then when we actually go to the chemistry lab and do something, sometimes, well, most of the time, we don't get to the 100% yield. Sometimes you go over 100%. Like, why would you go over 100%? Like, maybe your sample's wet, and then you weigh it at the end, and you have, 110%. Like my old football coach, you got to get 110%. Well, I guess you can in chemistry class, but if you do it improperly and end up leaving solvent like water on the product, then yes, you can give 110%. But it's usually the other way around, where you get less than. And the reason is, like, say that you're making something like iron from iron ore. Well, iron ore is not pure iron oxide. It's got other stuff in there. It's got slag, for instance, and so because it's not pure, you're going to have a little bit less product from that, and that's why we have a certain amount of yield. But anyways, we'll get to actual yield later. Start with a theoretical yield. That's the most that we can actually make. And like I said, the percent yield. Well, we did something in the pizza example. You burn a pizza, you something like that, and then you have to throw it out. So the actual yield. So if we have enough stuff to make 3 pizzas, but we burn 1, so we actually got 2 pizzas, which means that we had an actual yield of 67%. But then the chemical reactions, various things. So similar ideas. We have limiting reagents, but we always have other things in excess, unless it's completely perfectly aligned, but that's very rare for that to happen. We almost always have something in excess, and then the product. Well, using the limiting reagent, we get the theoretical yield, and then we get the actual yield. So the limiting reactant or limiting reagent, it's going to be completely consumed, assuming you let the reaction go to completion. And anything in excess are just there. So what do you do with the excess? You can recycle it, for instance, in a chemical reaction. So theoretical yield is the most you can make of. The actual yield is what you actually get, and that's determined by experiment. And the percent yield is the actual over theoretical times 100%. So let's calculate this out. So here, if you remember here, this is the combustion of methane. And we have 5 molecules of methane and 8 molecules of oxygen. What's the limiting reagent? Well, from this, so we look at the product. So 5 molecules of methane will make 5 units of CO2, and 8 units of oxygen will make 4 units of CO2. So that means that oxygen is a limiting reagent. So, and that also means that methane, CH4, is in excess. So let's look at here. We have this equation here. Nitrogen plus hydrogen, 3 hydrogens makes 2 ammonias. And in this vessel, we have 8 molecules of hydrogen and 2 molecules of nitrogen. So what's going to happen? So the 2 molecules of nitrogen can make 4 molecules of ammonia. The 8 molecules of hydrogen, well, because it's a 3 ratio, 6 of them are going to react and 2 are going to be left over. So with that. And then the answer for this is actually C. C is the is what we can. I mean, these are using individual molecules. It's usually going to be moles, which you can go into fractions. So when you calculate this out, well, I mean the theoretical yield, the actual yield is something you measure, or it's given to you in a problem. But to do this, you can do the limiting reagent and a theoretical yield using dimensional analysis. So let's look at this. A mixture contains 24.5 grams of magnesium and 33.8 grams of oxygen. What's limiting reagent and theoretical yield? So we have to figure out which one produces the smallest amounts. So magnesium and oxygen, we have to do 2 problems to figure out how much product we have. And then doing this magnesium, so we convert moles, the 24.31 grams for magnesium, that comes from the periodic table. And then converting the stoichiometric ratios between magnesium oxide and magnesium, we find we get 1.75 moles of magnesium oxide from that. And then with the oxygen, 33.8, then that's the molecular weight of oxygen. So 16 times 2 from the periodic table for oxygen, so 1 divided by 32. But it's a 2-to-1 ratio for magnesium oxide to oxygen, and we get 2.1 moles of magnesium oxide. So the magnesium is a limiting reagent. And okay, so let's move on. Nitrogen dioxide reacts with water from nitric acid and nitrogen monoxide by this equation. So we have 5 moles of NO2 and 1 mole of oxygen combined. How many moles of the reactant excess are there after the reaction is completed? So 5 moles of nitrogen dioxide, but we only need 3 of them. If there's 1 mole of water, you only need 3. Well, if you go by the ratio, right? So the 1 mole will produce. What are we looking for? Okay, we're just looking for any product. So one mole of water will completely react, and to have the 1 mole of water completely react, it needs 3 moles of NO2. If 5 moles of NO2 react, we need 5/3 moles of water, so 1.67 moles of water. So from that, you can see that the water is the limiting reagent, and if that consumes 3 moles from that, the 5 minus 3 moles is 2 moles left over, 2 moles of NO2. So combustion reactions using oxidize are usually oxygen, and they are usually, they're exothermic, so emit heat. And we've used this example several times, the combustion of methane. So another example is ethanol. So you can burn ethanol and oxygen to form carbon dioxide and water. And some other reactions, so alkalis, we've talked about this before with sodium chloride. Sodium metal plus chlorine gas makes sodium chloride, and this is a vigorous reaction. Alkali metals, so we're just going to we talk about combustion. Let's talk about other types of reactions. Alkali metals also react with water to form hydroxides and hydrogen gas. These are also exothermic, and sometimes these explode. So you can look on the internet if you want to see videos of alkalis. Sodium especially tends to explode. So here you have lithium, sodium, potassium. I know I just said that sodium explodes more. Potassium's more rigorous, but since sodium's a little slower, actually sometimes the sodium sinks and then it detonates, and you can get larger explosions from hunks of sodium, actually. Halogens, so these are the salt-forming. Remember, halogen means salt-forming, and I guess I didn't say what salts were. Salts are they're the result of an acid-base neutralization reaction. They're also a metal and a non-metal that are not a hydroxide or oxide. Those are the 2 definitions of salts in the chemistry class. But these react pretty rigorously. So react with metals to form metal halides. React with hydrogen to form hydrogen halides. So a halogen halide, that's where the word halide comes from. And also halogens can react with each other to form interhalogen compounds. And here's what some of them look like. Problem with fluorine eats through glass, so that's why you're not seeing fluorine in the gas But chlorine has a kind of a lime green color, bromine has kind of an orangish color, and iodine has kind of a purple color. Okay, see you next chapter.